Hi again, my dear students, and welcome back. We're going to continue on the stacks, this time using linked lists. We're going to continue what we have started last time in lesson number 19. And in this lesson, number 20, we're going to just continue with the different operations we perform on stacks. So basically, the thing we're going to cover in here is more on stack operations. Basically, to redo all the implementations that we have done before, but using the linked list implementation this time. Last time we talked about was on the array implementation. And at the end of this presentation, we're just going to make a very brief comparison between the linked list implementation versus the array representation. Limitations, advantages, and disadvantages. Okay, the pop operation. Remember last time we talked about creating a list, which is the stack, and then we talked about pushing to the stack. We're going to continue from there, and the first function we're going to talk about is pop operation. Pop operation means retrieve information from the stack. Take the first entry on top of the stack, okay, for processing. So basically, to us, it's like a delete operation from the top of stack, and top of stack always. And top of stack, as you all remember, is pointed by the top or head pointer. So basically, if I would like to retrieve this entry on top of the stack, okay, then what I'm going to do, as we all remember, I'm going to just make this pointer pointing to the next entry here, okay, and then destroy this after I copy the contents to some storage area for processing. Right? So before, it will be something like this. After I perform the pop operation, this is going to be gone, and this pointer is going to be pointing here, and more than this will be 2 now instead of 3 as it shows here. This is a little mistake because I have to adjust this always to point to the number of entries that I have. So what I have now is just 2 entries, and this is a pointer that points to the first entry now on top of stack, which is blue instead of red. The content here will be removed into an item for further processing, as I said, and then the structure, the space allocated for this node is going to be destroyed, freed. Okay, let's develop the function to do that. The prototype for the function looks like this. The name of the function is Bob, and it's going to return an integer value. And again, this integer value is used to say the operation was successful, 1, or unsuccessful, 0. Basically, what I need to pass to this function, as before, is the item, and this item is basically some variable that I'm gonna put in it the content of the node on top of stack. And because I'm gonna change its content basically, that's why I had to pass it as a pointer of this type of stack entry type rather than value. Again, because we're gonna change it. And then, of course, I'm passing the stack structure S, from which I'm going to retrieve the information. The precondition, well, the only assumption we have in here is that the stack S already exists and it's not empty. Okay? Because if it's empty, then I will have the problem of underflow. Then I have to check first that I have entries to start with, and then I will remove the entry on top of the list, place the data in item. Post condition, well, after successful return, the entry at the top of stack will be removed actually from the stack, and the data in there is going to be returned into this location pointed by item. And the return value is going to be 1, indicating that it was a successful operation. All right, let's look at the C code then. It's very simple, very straightforward. Like the delete code we had when we talked about linked lists. However, this is a very special delete to where all my deletions are going to be from the top of stack. Of course, before I destroy or delete the entry, its content is going to be copied somewhere else in item. All right, what am I going to do? I'm gonna use the local variable called delete or del ptr, which points to the entry on top. And why do I need this? Because once I remove the top, it's going to go to the rest of the list, and I need to have a pointer pointing to that node to be able to free it. Otherwise, it's going to be like a bubble in the memory structure, and I won't be able to free it again. So basically, the picture is something like this. Here's my list representing the stack. And here is my top. And there is, of course, count, which contains the number of these entries in here. I would like to delete this item. So basically, I need to point to it. And that's why I'm defining this variable, local variable, del ptr. So del ptr in the first place is going to point to this first entry the same way as top is pointing. Okay, and then I'm going to perform the delete operation. Let's see. I'm making a check first to verify that the list to start with has some entries to retrieve. Okay, so I'm saying if count equals 0, that means the stack is empty. Okay, so I'm not going to be able to retrieve anything from the stack. So just return, don't do anything. There is nothing actually to retrieve from the stack. But this is an unsuccessful return in a sense that I did not retrieve any data and I did not put anything in item. All right, that's why I say in here return 0. The stack was empty. Okay, so I avoided the problem of underflow this way. Otherwise, if there is data and count was not 0 actually, then I'm going to perform this retrieve operation or pop operation. What am I going to do? The first step I'm going to do is make this pointer point to wherever top is pointing. And it's exactly assigning this pointer down here. Okay, so I'm making del ptr equals to s arrow top, to wherever top is pointing. That's the first step. The second step, I'm copying the data inside this into item, because that's actually the data I want to retrieve. The node itself is the container that contains the data, and the user wants to process, to serve the data inside it, not the container. And that's why I want to take the data into item and then destroy the container. All right? So after I do this step, I'm going to take whatever in the stack pointed by top, the data in there, the entry, all right? Take that and place it in the memory at the address pointed by item. This could be just a single step like this, or it could be many steps, of course, just a copy. It depends upon how many variables I have physically that comprise the data. All right? And what do I do after that? Basically, I'm going to make top point to the next node in the list. And that's why this is step number 1. Step number 2 is to take the data into item. So this is step number 2. And now step number 3 is to make this point here. All right? Instead of pointing to this first container or this first node. Okay? What do I need to do after that? Well, step number 4 is I need to destroy this entry. So what I'm going to do as step number 4 is take this and delete it. This is step number 4. All right. So that's the first step. Second step, copy the data. Third step, advance the top pointer to go to the next location. And then after that, I'm freeing the node pointed by del ptr, this one. Okay? And of course, before I leave, I have to remember that now the list has one less item than it had before I enter this function. So count is going to be decremented by 1. Okay? And after this, this is a successful return, so I return 1. All right? Very simple, very straightforward, nothing new in there. It's just basic manipulation of a linked list. Okay, let's see another function, stack top function. Stack top function, if you all remember it, it's the function to where I would like to just copy the entry on top of the stack, put the content in item, but leave the stack as is. Don't touch it, don't change any of the entries in there. Okay, so the stack is going to remain the same as a result of this. However, the data in the first node is going to be copied somewhere else. Okay, and I said earlier that this kind of function is needed in some applications to where I would like just to check, process the data, do something with the data, and just leave it as is. I'm not doing anything, I'm not touching, changing the data inside the list. Okay, so to do that, I will need something like this. Here's my list representing the stack. And here is top that points to the beginning of the stack. Of course, there's count again. All right, what do I need to do? Well, simply just go in there and take whatever data you have, copy it into item. And that's it. Basically, one step. Could be one simple step or one major step to where I would like to copy several items, several variables comprising the data in here. That depends, of course, upon the structure defining the node. Okay, so basically the prototype will be something like this. Integer stack top. It takes as an input a pointer to item, and this is the container that's gonna carry the data I'm gonna retrieve from the top of stack, and of course the stack itself, a pointer to the stack. The precondition, simply as with the previous one, that the stack already exists and it's not empty, because if it's empty then I'm afraid I cannot retrieve anything from an empty stack. So I have to check again, all right, to see if there are any entries inside the stack, and then perform this copy operation. As a result of this, the item at the top of stack is copied, and only copied into item without being removed. I'm not going to remove it. No deletes, no changing of pointers. Everything is going to stay the same. The basic structure is going to stay the same. Okay, so after this step, the stack remains the same. This function is going to return 1 upon successful, as I said, and it's going to return 0 otherwise. Here's the code for it. Very simple, straightforward. Here's the definition of the function. Okay, and what I'm saying in here is if count greater than 0, that means I have entries in there, then you can copy. Otherwise, return 0. True? So in the if clause, I have these statements from here to here. Take whatever entry pointed by top. Okay, so go to S, arrow top, arrow entry inside this. Take whatever data in there and place it in the memory pointed by pointer item. And then return 1, simply. That is in case when I have count greater than 0. However, if count equals to 0, that means the stack is empty, and in that case, I'm going to return 0, saying it's an unsuccessful return. Very simple and straightforward. Another function, stack empty. It's a Boolean kind of function to where I would like to check with a yes or no. Is the stack empty? We used to do the check actually in the previous two functions, but sometimes we would like to have it as a separate function. So why not implementing it and make a call to this function whenever there is a need? Okay, basically it's going to take the stack only as the only entry, and its return value is going to be of type Boolean. That means true or false, 1 or 0. How am I going to check? Well, simply, if I have the structure for the stack the same way I already defined it, where I have count, then simply the stack will be empty if count equals to 0. Okay, otherwise it's not empty. All right, so if that is the case, then I'm just going to be looking at count here. I'm not going to look at any entries in there. All right, so the way it's going to go is something like this. As a precondition, it assumes that the stack is already exists and has been initialized, and the postcondition, as I said, is to return true if the stack is empty, otherwise it returns false. Implementation, very simple, one line of code. Okay, Boolean, stack empty, takes a stack, a pointer is to the stack, and I'm just going to return the result of this logical expression. Is count equal to 0? If that is the case, true, 1, it's going to return 1, returns true. That means the stack is empty. If the result of this expression is false, then the return value is going to be 0, and then this is an indication that the stack is not empty. Well, however, if the definition of a stack does not contain this integer count, then how would I know if the stack is empty or not? Well, again, it's very simple. All I'm going to do is check where top is pointing. If top is pointing to null, that means I don't have any nodes along the stack. And in that case, I'm going to return true. If top is pointing to something, anything other than null, then that means there is something in the stack and the stack is not empty, so return a false. Okay, so whether I have this count or I don't, it's just one line of code. It's just a matter of what I'm checking and what I'm looking at when I make the return value. Stack is full. Okay, let me stop in here before I continue with the prototype and the precondition, postcondition thing. Will my stack be ever full? Well, our claim was that we're going to be using linked lists rather than arrays, because there is a limitation on the arrays in a sense that you have to determine what's the maximum size of the array ahead of time at the beginning of your program. True? And then at that time, we said we're going to develop a function which says stack is full. And that's when I attempt to enter a new entry where my array is really full with all entries. Fine. What does it mean in this case? Well, it means the following, as a matter of fact. Yes, there is no restriction on the size of the stack, and it kind of grows the way it likes. However, there is a limitation, which is the memory space available in the computer, as a matter of fact. I have 1 meg worth of RAM, 2 megs, 10 megs, I don't know. Well, this RAM is being used by this program and maybe by other programs. Okay? What does that mean? Well, that means anytime I'm unable to allocate memory, further memory for further nodes, that means the stack is full. All right? And that's when I will return a true as a result of this function. Okay, so it's not a rigid, actually, limitation on the structure. It's not a limitation on the data structure that I have physically to implement or to represent the stack, but rather it's a limitation on the size of memory and the amount of free memory available for this application, and what is on the other side, the memory that's already reserved and used by other applications. Okay, so in that sense, yes, I could have a full stack. How to check for that? Well, simply, I will make an attempt to allocate memory for a node. If that was successful, then my stack is not full, and I have still room for other nodes to be located in the memory. However, if I could not allocate memory anymore, that means there is no memory space for this application, and in that case, I will return back the Boolean true value saying that, sorry, the stack is full. Okay, based on this, then to check whether my stack is full or not, then I'm going to have this parameter only, the definition of the stack, pointer to the stack, okay, as the only parameter I'm passing to this. And this function stack full is going to be of type Boolean. The precondition for this is that the stack already exists and it has been initialized. All right? And then the post condition, it's going to return true if the stack turns out to be full or false otherwise. let's see the implementation. The implementation, as I said, is going to check for the availability of extra memory, okay? And I'm going to attempt to allocate, all right, for a node. If I manage to do that, then okay, there is space. Do I keep that allocated space? No, I did that just for checking. So just free it before you go home and return true. Return false. There is still space. If the malloc function failed to allocate memory, then in that case, the memory is full or the stack is full. So let's see how we're going to implement that. I'm going to define the variable temp to be of type pointer to a node, stack node. So I'm going to try to allocate space in the middle of this program for temp. Okay? So I'm saying here, if temp equals malloc size of stack node, and this is the cast value to return a pointer of this type. Okay? So what I'm trying to say in here, allocate memory, this much of memory, the size of the stack node, okay, and make temp point to it. Well, if the malloc succeeds in doing this, then the return value in here is going to be something other than null. Okay? If it fails, then the return value is going to be null. All right? So I'm checking if the result of this malloc operation is something other than null, that means there is still space. Okay? So the stack is not full yet. So what I do in that case, again, I'm not going to keep the space. I just did this allocation just to test the space in the memory. So in this case, I'm going to return 0, indicating that the stack is not full. I still have place to accommodate new customers. However, if the malloc fails, then I'm going to get here. And in that case, the malloc could not allocate any more memory in the space. The memory is full, either by this application, by this function, or by any other application or any other function. In that case, yes, the stack is full, and please return 1, indicating a true value. Okay? So that's what we did. And remember that we had to free temp here, because it was just an exercise checking the memory, the status of the memory. All right. The other function we would like to talk about is stack size. Again, stack size is basically a return value of integer, which tells me how many entries I have inside the stack. Again, if we define our stack to have the top pointer and the count integer, then simply this function will just go and return the value of count. Just one line piece of code. Okay? If that count is not part of the definition of the structure representing the stack, then we have physically to start from here, okay, traverse all the nodes in the list till I get to null. Each time along the road, I will just increment my counter by 1. Okay, and then whatever counter I end up with after I reach null is going to be my return value. So it's either this or that. It doesn't matter. Let's see how we're going to implement this function. Integer, the return value, and that's basically going to carry the number of entries in this list. The name is stack size, and as an input, it takes the stack structure pointer. The precondition for the function is the stack is saying, indicating that it exists and it has been already initialized. The post condition, it returns the number of entries in the stack. All right, let's see the implementation. Well, the implementation is very simple because I'm assuming here that I'm using this structure I defined for a stack, and in this structure I basically have this count entry. So basically, just return is arrow count, and that contains the number of entries, and that tells me the size of it. However, if I don't do this, then I need to do something like this. If I don't have this count variable in the structure, then I need to define a variable of type stack node. PTR, and initialize it to be something like S arrow top. Okay? And I need to define a local variable integer counter, which basically gonna count the number of entries I have in there, and I'm gonna initialize it to 0. All right? And then, since it's already pointing here, I'm just gonna say, well, if I'm pointing already here, I could count this already and say in here 1 instead of 0. It depends upon the way we're gonna increment. I could increment before or increment after. All right? And then basically, I will say while PTR arrow next, or capital N to be consistent with what we had, while this does not equal to null, then what do I need to do? Counter equals counter, counter plus plus. Okay? So I will only count if the next entry is not actually null. Okay? And that's it. That's basically the what I have in this while loop. And then I'm going to return counter. Something like this, actually, and I just return. Maybe we need to check for this first one to check whether I need to start from 0 or 1, but that's not a big deal. You can check that yourself. The last function I would like to talk about is how to destroy a stack. Destroying a stack means that I have to delete all entries in there and even to destroy the pointer pointing to the stack itself. S, what we used to call S in here. And I just, in this function, would like to just remove from the memory everything about this stack. I don't want that stack anymore. Well, basically, this function is going to be of type void, and it's going to take as its input a pointer to the stack. Okay? And as a precondition for this, I'm assuming that this stack is already exists and it has been initialized. It has some entries inside it. All right? And as a result, all entries will be removed and the stack itself will be removed as well. Let's see how we're going to implement that. Okay, void, destroy stack, and it takes as input a pointer to the stack. All right, to be able to destroy, I need to destroy every single node in there. And that means I need to delete or free the space allocated by every node in there. The easiest way to think about this for beginners is something like this. Here's my list. And here is top. Well, what if I do something like, first, this is part actually of S. So S has actually inside it top and count. What if I say something like free S? What happens? Or what if I say something like make this point to null? You're asking about the stack, right? And I don't see any stack now. It's pointing to null. It's all gone. Fine, you don't have any stack. However, these entries are still existing in the memory. And that's the worst kind of solution you might think of. All right? Yes, the structure is gone now, either by destroying S, by freeing S, the space for S, or by at least making top pointing to null, but these guys are still sitting in the memory, okay? And nobody can use this space just because of them. And I'm afraid you can't say sorry after this step, and you cannot actually correct this big mistake because simply you don't know where those people are located physically in the memory. So once you do this, we're in a big problem actually in terms of storage, in terms of memory. All right? So whoever asked you to destroy the stack, you showed him that stack is pointing to null, no entries in there, but God knows what's inside the room. A big mess inside the room, and nobody can clean it. Okay? So this is not the solution actually for it. Never do this. Never ever do this. How to do it then? Well, let's think about it. I need to start from the very beginning. Okay? Visit every node. And with every node I visit, delete it. And go to the next, delete it. Well, if I delete the current node, then again, I cannot go to the next node. So somehow I have to keep a pointer pointing to the next before I destroy this one. Otherwise, this and the remaining ones are going to be somewhere in the memory, and I cannot free them after that. So what we're going to do, we're going to define a local variable called delete PTR, pointing to a stack node. And I'm saying here, if S does not equal to null, that means I have entries in the stack, then before I can clear the stack itself, destroy the stack structure itself, I need to go to the nodes, delete them one after the other. Okay, so what I'm saying, while top does not equal to null, S arrow top does not equal to null, there is something in the stack. Okay, make this pointer points to top. So put this pointer, delete pointer up here at the beginning. And then let top move forward. Well, I don't care about usually we never actually move this one from here, okay? To keep everything actually together. Well, I don't care about this step anymore. I don't care about the list because I'm destroying the list anyway. So I will move top forward. Okay, so I will make, so this is step number 1, to put this temporary pointer, and step number 2 is to make this point here. Why I'm doing that? So that the rest of the list is still in my hand. Okay, and now this node is pointed by this pointer here. Okay, no, you can now safely free this space. Okay, and then now top is pointing here. Make this pointer, temporary pointer, to point to here and move head forward or top forward. Again, free this. So each time in the process, what I'm doing, I'm having 2 pointers actually. One pointing to the rest of the nodes so that I don't lose them, and one is pointing to the current node and I free it. Move forward and then to the next and free. All the way along the road till you get to null. So I will keep advancing this one forward each time till I reach null. Okay, but before I reach that null, I will always move this pointer to where top is pointing and then advance pointer top to point to the next entry. Okay, and then after that, free the current node pointed by PTR. Excellent. And that's the end of the while, basically. All right? So these 2 pointers are going to help me along the road. One, which is top, keeps track of the rest of the nodes, and this one to delete the current node, and I advance them in the fashion I just shown in the slide and the previous one. Okay? Well, I will keep deleting these items one after the other till I reach the end. Okay, everything is destroyed now, except for the structure actually defining the stack itself. I have a structure in here, actually, which contains this top and contains count, according to our definition. And this pointer actually pointing here. Yes, now it's pointing to null, as I advanced it step after the other, deleting all the nodes along the road, but still I have space allocated for this. So the last thing before I return is to destroy this as well. And this is the last step I do in the process in here. Free S. Okay? And again, remember, I do this at the very end. I don't do it at the beginning. Okay? Because if you do it just like this, with this line only, that's like a fake delete because entries are still in the memory. All right? So this is the last step I do, and after this I can safely return, and the whole structure, which is called stack, is destroyed. We have built it along the road, made many pushes, make many pops, did whatever we did with it, and now at the end of the day we're all tired and we just want to get rid of it. All right? And that's the destroy function. Okay. The very last thing we want to just look at in here is just a quick comparison between the array implementation, which we covered a few classes ago, a few lessons ago, and the implementation which we did in this lesson and the previous lesson using the linked lists. Array implementation and linked list implementation. What are the differences that we have in this implementation and that implementation? Well, number one, there was a limitation actually on the number on bounds. Which implementation suffers from this limitation? It's the array. Why is that? Because when I defined the structure that will hold my stack, I had to define the maximum number of entries. And I have to determine this at the very beginning of my program. What is the problem with this? If you all remember, the problem with this is either the overflow, and that's when I have too many customers coming and I did not make my preparations for all of those people to come, and then I cannot accommodate those customers. And the other problem is the problem of poor utilization. Of the memory, and that's when I have allocated a huge amount of space, and during the execution phase I realized that I don't need that much. I don't have that many customers to come to my stack. Okay? Do I have this limitation in the case of the linked lists? Of course no. Simply because I don't have this max number of nodes at all at the very beginning. I create the node only when there is a customer. Okay? So I don't build the fancy hotel with thousands of rooms, assuming that I'm going to have enough customers to come to me, but rather, whenever I have a customer, I will build a room for him. Okay? When the customer leaves, I will just destroy or free that room. Okay? Clean the space. And that's a more efficient way of handling the memory. However, there is an advantage for arrays over linked lists. What is that? Well, in arrays, I can access any location in the array anytime I like without going to all previous entries or locations in the array. That's basically random accessing. I don't have that, unfortunately, in the linked lists. Always linked lists, if you're going to access them, you have to access them sequentially. And that's why if you need to search for somebody, it has to be a linear search. Linear search means an average number of operations of n over 2, where n is the number of entries that you have in the list. Whereas if I'm talking about array and that array is ordered, then I can use binary search rather than sequential search. And in this case, I will have an order of log n to the base 2 rather than this big number. And of course, there is a big difference between these two, especially when n is very large. So whether in a linked list the numbers are already ordered or not, there's no difference at all, and because I'm going to do always sequential search rather than a binary search. As well, at any time, to access any location in the linked list, I have to go sequentially. And I have to be always careful about these pointers when I insert and when I remove and when I push or pop from the stack. Thank you very much for watching. That's it for today. We'll see you next time. Of course, if you'd like to refer to this material, go to the UNINETTUNO website, click on the MidNetU project, and you're going to find lots of interesting stuff. Thank you for watching. Bye-bye.